everyone. So in today's video, we are going to continue to talk about derivatives, kind of changing our viewpoint a little bit with the way that we're thinking about them. So we're now going to be in section 2.8, and we're going to be thinking of this idea of the derivatives. Remember from last time that the derivative at a certain point in a graph is the slope of the line tangent to the graph at that point. And so today we're going to be kind of stitching together all of those different derivative values and seeing that if you kind of put them together, they give you actually a function called the derivative function. So as kind of a warm-up, I want to look back at, this was like, I think the first example we did in our video on Friday, f of x is equal to x squared. And I want to calculate the derivative for a few different values of a. So we're going to kind of fill out a table here where we have different values of a, and then what the derivative is at that value. So we already did, in last time's video, we did the tangent line at 1. So I want to do -2, -1, 0, and 1. So we already saw last time that if you take the derivative of f of x is equal to x squared at 1, we saw that you got a slope of 2. So we're not going to redo that one, but I do want to do the other ones. So as a warm-up, I would encourage you to pause the video and go through yourself using the limit definition to figure out what is the derivative for -2, for -1, and for 0. And then once you finish that, you can unpause it and I'll go over together how to do that. Okay, so remember from last time that the way that you can find the slope of the line tangent to the graph at a certain point is you take the limit as h approaches 0 of f of a plus h minus f of a, all divided by h. So just to remind you like where that came from, the idea was that if you look at this part of the equation, or the limit, this would be the slope of the secant line between one point f of a, or one point a f of a, and another point where it's just a little bit past a, so a plus a little bit more. So if you write out the slope of that secant line, it simplifies, the denominator simplifies to just being h. And then why are we taking the limit? Well, we're trying to bring this second point closer to the first point. And so that means that we're trying to take this h and bring it closer to 0, because the closer you bring h0, the closer the second point, a plus h, the closer that gets to just being a. So let's do a few of these together. So for example, if we do f prime of -2, that would be the limit as h approaches 0 of f of -2 plus h minus f of -2, all divided by h. And so in this case, the function is taking your input and squaring. That's all it is, right? F of x is equal to x squared. So we have -2 plus h squared minus -2 squared, all divided by h. And so that's the limit as h approaches 0 of 4 minus 4h plus h squared minus 4 divided by h. And so as should happen with these types of limits, that you should find that some stuff cancels out. So specifically here we see that we have a 4 and a -4, and so we're left with just -4h plus h squared divided by h. And the nice thing about that 4 canceling out is that now we are left with everything having an h in it. So we can actually divide everything by h. So we have an h down here, we can divide the first thing by h, and then the second thing will become just h and h squared. So we have the limit as h approaches 0 of, now it's just -4 plus h. And now we can actually plug in 0 for h, and so we just get -4. And so we just figured out that the slope of the line tangent to the graph at x is equal to -2 is -4. So that would mean that if we were to go to this point on the graph where x is equal to -2 and sketch a tangent line, it has a slope of -4. Okay, so let's do a couple more. I know this is a little bit repetitive, and we'll see shortly that there is an easier way to do it, but I just want to give you a little more practice with this. So I'm going to skip writing this part on this one because it's basically the same. So I'm going to jump right to when we're plugging in our into our function. So we have -1 plus h squared minus -1 squared, all divided by h. So now we have 1 minus 2h plus h squared minus 1 divided by h. And so again, these 1's are going to cancel out with each other, and we're left with the limit as h approaches 0 of -2h plus h squared divided by h. Same as before, we have a common factor of h. So now we're left with the limit as h approaches 0 of -2 plus h. And so now we can just go ahead and plug in that 0 for h, and so we're left with just -2. So now we found that the slope of the line tangent to the graph of f of x is equal to x squared at x is equal to negative is -2. And that kind of makes sense if you think about it. So if you look at, we knew that at +1, the slope was +2. So that would be the tangent line there. And what we basically just figured out is that if you go to -1, the slope is -2. And that makes sense because the graph is symmetric, right? It should be negative on one side and positive on the other, but should also have kind of the same steepness. Okay, last one's going to be a little bit faster. So the last one I wanted to do was 0. So if we do this at 0, we're going to get 0 plus h squared minus 0 squared, all divided by h. So that limit as h approaches 0 of this, the whole thing basically just simplifies in the numerator to just h squared over h. And so that's the limit as h approaches 0 of just h, because we can do some simplification. And now we can just plug in 0 for h and we get 0. Okay. So, and by the way, that's not too surprising, right? Because if you look at the graph, if we go to x is equal to 0 and draw the tangent line, it looks like a horizontal line. And a horizontal line has a slope of 0. Okay, so looking at these numbers in our table, notice they kind of have a pattern to them, right? It goes -4, -2, 0, 2. They keep going up by 2 each time. So I actually graph these points. And so there's one thing I'm just going to quickly change, and it's really not a big deal. You're allowed to use whatever letter you want for a variable. You could say, so what I basically want to do is I'm going to change both of these to x's. Oops. And that doesn't really matter, right? I can use x, I can use a, I can use whatever letter I want. The reason I'm going to use x is we're going to graph these now, and I think it will just kind of be a little bit more consistent with how we typically graph things if we call the input x. So the way that I'm going to graph these points is for each x value, I'm going to take the derivative value we got and plot that as the y value. So for example, we have the point -2, -4 is on our graph. And then when x is -1, we found that the slope was -2. So I'm going to plot a point at -2. At 0, we had 0. And at 1, we had 2. And so if we connect these, we can start to see that it is a line, right? And it turns out actually, and we'll see this for sure in a little bit, basically, if you stitch together all of these derivative values, you're going to end up with a function that is just the function 2x. And I'm not sure, that might not be on the screen, so let me actually move that over a little bit. So basically what I'm saying here is that you can take all of these derivative values and kind of forget about the original function for a second. Just think of this as its whole own new function. So our new function, if you wanted to, you could even call it g of x if you didn't want to have the f prime. So we have a new function, and that function is 2x. It's just a line that goes through 0, 0 with a slope of 2. So this is called the derivative function of f of x, and I'll write that down as kind of a more general fact in a moment. But basically, there's an easier way that we could have done this. So how did we figure this out? We basically did the slope of the tangent line at all these different x values, and then we kind of just looked at them and said, oh, well, we can kind of see a pattern here. But there's an easier way to do this. What we could have done is, instead of doing individual slopes for every different value, what we could have done instead, so let me just write this out. So instead of calculating f prime of a separately for each individual x value, right, for all the different x values or a values where we're trying to find the tangent lines, we can do it all at once. And so when I say do it all at once, basically, this will give us a formula that will tell us the slope of the tangent line at any x value, not just at one particular x value. And so the way that we're going to do it is basically, instead of just putting all the different numbers there, we're going to do the exact same formula that we did before. So the limit as h approaches 0, the only difference is I'm going to put an x instead of an a, because that's kind of the variable that we're focusing on now. And we're not going to actually put a number in for x. We're just going to leave the x there. So let's see how that works out for this particular function. So our function is f of x is equal to x squared. So I just want to write one thing out first to kind of help us simplify this. So our function is f of x is equal to x squared. That means that f of x plus h is going to be x plus h squared. So a little bit trickier, because now we have two different variables, but it's still the same kind of deal as it was with the other one. So if we multiply this out, we get x squared plus 2xh plus h squared. So I just wanted to write that out ahead of time, so when we go and do our limit, we don't have to do that on the spot. Okay, so if we put that in, we have the limit as h approaches 0 of f of x plus h minus f of x over h is going to be equal to the limit as h approaches 0 of, so f of x plus h ended up to be this thing, so we're going to put that in here. So we get x squared plus 2xh plus h squared minus, and f of x is just x squared, right? That's the function f of x is equal to x squared over h. And so the next going to happen is actually going to be extremely similar to what happened on all the examples above. So the x squared and the x squared are going to cancel out with each other, and we'll be left with the limit as h approaches 0 of 2xh plus h squared over h. And just like in the examples we did above, now we have this common factor of h that we can cancel with the denominator. And so now we're going to get the limit as h approaches 0 of 2x plus h. And so now we can plug in 0 for h, and we just get 2x. And if you look back at the examples we did up here, it's literally the exact same thing. We canceled out the same stuff. And the only difference is that now what we came up with is, now we have a general formula that will tell us the slope of the tangent line at any x value. So if you do, rather than doing all of those separate things, you can just do this once. And once you do it once, now you can plug x values in to find the slope at that particular x value. So now we know that our derivative function, so f prime of x is equal to 2x. And this gives you the slope of the line tangent to your original function f of x at any x value. So for example, let's plug in one that we actually know. So we know that the slope of the tangent line at 1 is supposed to be 2. So if we plug in 1 into this function here, we get f prime of 1 is equal to 2 times 1 is equal to 2. And that lines up with what we expected. But we could also do some other ones that we don't know. Like let's say you wanted to find out what's the slope of the tangent line at negative 0.6. Well, you would plug that in and you would find that it's 2 times negative 0.6. So it's apparently negative 1.2. Let's say that you wanted to find the slope of the tangent line at x is equal to 100. You could plug in 100 and say, okay, it's 2 times 100, so it is 200. So it's very steep, which probably isn't that surprising because if you think about what a parabola looks like, it gets steeper and steeper as it goes. So basically we cooked up this, this thing that is now going to be called the derivative function that isn't just telling us the slope of the tangent line at one x value, it's giving us a formula that can then tell us the slope of the tangent line at any x value we want. So I'll define that kind of more generally in a moment. I want to, before we do that, just go back quickly to the pictures I have here, because one thing we're going to be focusing on both today and in the future is kind of comparing the original function and its derivative function and trying to look at some kind of connections between them. So one thing that has come up a few times throughout the quarter is this idea that if a function is decreasing, so if it's going down from left to right, so notice that our function, our original function here, oops, let me make this a little thicker. Our original function here is decreasing on this part of the graph, right? From basically negative infinity all the way up to 0, it's going to be decreasing. And so if you take the slopes of the tangent lines at any of the points on that part of the graph, they should come out to be negative, right? Like the slope of the tangent line at any of those points is going to be negative. And so what that means is that if you look at the corresponding part, and maybe let me just kind of circle this so we know like what part of the graph we're talking about. If you look at the corresponding part of the derivative function, it's negative, right? This part of the graph is negative. And when I say it's negative, I don't mean anything about whether it's going up or down. I literally mean the y values are negative. So the actual function values of this derivative, if we just think about it as a function, it lies below the x-axis. So the function itself is negative. So now if we look at the right-hand side of the parabola, this is a function that is increasing, right? It's going up from left to right. So if we were to take the slope of any of the tangent lines on this part of the graph, they should be positive. And that shows up with what we see here, because if you look at, this part of the graph, all of the y values are positive. And then if you look at the at what's going on at 0, so if we were to go like here, at 0, it's neither increasing nor decreasing, right? It's just kind of flat. And so the point on the derivative function where it is neither increasing nor decreasing, it's not positive, it's not negative, it's actually equal to 0. So we'll do a lot more practice with this in tomorrow's video, actually, kind of being able to compare the graphs. So I just wanted to kind of give that initial kind of comparison so you can start to get some intuition for how to look at the derivative and understand what it's telling you about the original function. Okay, so I want to write out just like a general fact, and actually, yeah, let me do it here. So we basically said all of this, but I just want to state it in general. So in general, if f of x is a function, and we'll see actually in, I think, tomorrow's video that there's some exceptions to there's some like restrictions on which types of functions we can work with, but for now, let's just say if f of x is a function. So if f of x is a function, then f prime of x is its derivative function. So basically, how does this derivative function work? If you plug any x value in as an input to the derivative, it will tell you, the output will tell you the slope of the tangent line at that point. So f prime of x tells you the slope of the line tangent to your original function f of x at any x value. And maybe let me write down something else just to make that really explicit. So when you're working with f prime of x, your inputs are just going to be, an x value. And the output, or the y value of your derivative function, the numbers that are coming out when you plug in an x, those outputs are going to be the slope of the line tangent to your original function f of x at whatever x value you're plugging in. So I know this is weird. It's like a different type of a function than what you're used to, right? Like you're used to working with functions that are like, oh, f of x is equal to 5x plus 3 or something like that. This is a different type of function. It's a function that gives you information about another function. So let me just also write down the general fact that we already said on the other page. But so to find the derivative function for a function, you're basically just going to calculate a limit. You're going to calculate the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. And the only difference from what we were doing before, again, is that you're not plugging in a number for x. You're leaving the x in there while you're taking the limit, and then later you can plug in x values once you have that general formula. Okay, so I want to do a few more examples, or a few examples of finding the derivative function, and then again, kind of comparing the graph of the original function and the graph of the derivative. So we're going to start with this function is f of x is equal to 1 over x. So by the way, this is a graph that I would expect that you kind of have some familiarity with what it looks like. So it's a very simple rational function. Okay, so what are we going to do? We are going to find f prime of x for f of x is equal to 1 over x. Okay, so how are we going to do this? We're going to use that limit definition. So we're going to do the limit as h approaches 0 of f of x h minus f of x, all divided by h. So that is going to be, in this case, the limit as h approaches 0 of 1 over x plus h. So we're plugging in x plus h into our function. And then we have minus 1 over x. So this is one of the functions where we want to make a common denominator, right? Because it's a fraction within a fraction. So let me open up a little bit more space for us here and make this a little more symmetric. So we're going to multiply this one by by x over x, right? Because we want to make a common denominator of x times x plus h. So x over x, and then we're going to multiply this one by x plus h over x plus h. So that's going to give us the limit as h approaches 0 of x over x times x plus h minus x plus h over x times x plus h all over h. So it looks a little intense right now, but the thing about these different methods we've learned is that basically they're always going to work as long as you don't make any mistakes. So you can just kind of trust that things are going to simplify out if you're doing your steps correctly. So when we put these two fractions together, one thing that I mentioned, I think in probably the last video, is to be really careful when you're subtracting a fraction. So when you're subtracting a fraction, the entire numerator has to be subtracted. So you have to put parentheses around it. So our numerator is going to be x minus parenthesis x plus h. And that's all divided by x times x plus h. And that's all divided by h. So limit as h approaches 0. So now this new numerator is going to be x minus x. So that's going to be 0. And then we're left with a negative h divided by x times x plus h. And all divided by h. So if you had forgotten to distribute this negative sign, you would have had a positive h here, and that's actually going to make our answer, that would give you the wrong answer. So now we're going to get the limit as h approaches 0 of, so let's rewrite this. Instead of writing it as dividing a fraction by something, let's rewrite it as multiplying by the reciprocal. So we can rewrite this as multiplying by 1 over h. And then if we're multiplying by 1 over h, well, now we can see that here you have an h, here you have an h, and those are going to cancel with each other. And we're going to be left with the limit as h approaches 0 of negative 1, because there was a negative sign here, divided by x times x plus h. And now we can actually plug in 0 for h, because now there is no standalone h in the denominator. So we're left with negative 1 over x times x plus 0, which is the same thing as negative 1 over x squared. So this tells us that the derivative function of f of x is equal to 1 over x is f prime of x is equal to negative 1 over x squared. So for example, let's say you wanted to find the slope of the tangent line to your original function at, let's say, x is equal to 2, well, you would just take this derivative function and you would just plug in 2. So you'd say f prime of 2 is equal to negative 1 over 2 squared. Okay, that's equal to negative 1/4. And that's going to be the exact same answer that you would get if you had done this limit with a 2 in it from the start. That was kind of the old way of doing it. But the value of this is that now you could plug in 5, or you could plug in whatever number you want without having to calculate a new limit. Okay, so I want to compare the graphs of our original function and the derivative. So this is our original function, and then I have the derivative one hiding over here. So let me just, sorry, my mouse went to sleep. Sorry, get it to work. Nope. There we go. So, whoop. Thought this would be easier. Okay, there we go. So that is the graph of the derivative function, so negative 1 over x squared. So I just want to point out a few things about kind of like the connection between these two graphs. So one thing I want you to notice is that if you look at the original function, if you were to take the slope of the tangent line at any point, it would always be negative, right? There's no place where this graph has a positive tangent line. So in other words, this function is always decreasing, right? There's no part of this graph where it's actually going up from left to right. And so that fits with the fact that the derivative function is always negative. If the derivative was ever positive, that would suggest that the original function would have a positive tangent line, which it doesn't. Another thing I want to point out is that the original function has an asymptote at 0, right? So if you go in and look at x is equal to 0, the original function is actually undefined at x is equal to 0. And so that means the derivative is also undefined at x is equal to 0. And we'll talk more about that tomorrow, but I just wanted to point that out. As the graph gets closer to x is equal to 0, so if you look at like the slopes of the tangent lines as you're going this way, they're negative, but they're becoming steeper and steeper negative. So like, for example, the slope of the tangent line here would be -1. And then if you go here, it's going to be like -4. I think that's one, or sorry, I don't know, we didn't do that one. But it's going to be something steeper. And if you go here, it's going to be even more steep. And here it's going to be even more steep. And so that fits with the fact that the graph, if you look at the y values of the derivative, they're just going down and down and down. And that's because the slopes of the tangent lines are getting more and more steep if you look at your original function. One other thing I just want to point out is that if you look going now this way at your original graph, if you compare the slopes of the tangent lines, they're getting kind of flatter. So here the slope would be 1. We did the slope at 2, that was 1/4. The slope at 3 would be, or sorry, -1/4. The slope at 3 would be -1/9. The slope at 4 would be -1/16. So the slopes are kind of getting closer and closer to 0. They're becoming these smaller and smaller fractions. And so if you look at the derivative is getting closer and closer to 0, but it's never actually reaching 0. And that's because the original function is never completely horizontal. It's just kind of getting closer and closer to horizontal. Okay, so let's look at one more example together. So this is now going to be f of x is equal to square root of x. So square root of x graph looks like half of a sideways parabola. Okay, so we are going to find f prime of x, the derivative function for f of x is equal to square root of x. So we're going to do the limit as h approaches 0 of f of x plus h minus f of x divided by h. So in this case, our function takes the square root of whatever is the input. So if our input is x plus h, that's going to be the square root of x plus h. And then we have minus the square root of x, and all divided by h. So this is one of the functions where you want to multiply by the conjugate of the part with the square root in it. So we're going to multiply this by the conjugate of this. And so the conjugate is just going to be the same thing, but with a plus. So x plus h plus 8, or square root of x over c. So when we do that part, so in the numerator, the square roots are going to kind of cancel each other out, and we'll be left with x plus h minus x. And then in the denominator, remember, you just kind of leave it and just be patient and know that something will cancel out, but you don't want to distribute it or anything. So in the numerator, the x's are going to cancel, and we're going to be left with just h. And then the denominator, we have h times the square root of x plus h plus the square x. And so these h's can cancel out, and we're left with the limit as h approaches 0 of 1 divided by square root of x plus h plus square root of x. And so now we can finally plug in h for, or 0 for h. So we have the limit as h approaches 0 of 1 over square root of x plus 0 plus square root of x. And so that is going to be, and sorry, I don't know why I wrote we don't need this limit part anymore, right? Because we already are plugging in 0. And so this is the same as 1 over square root of x plus square root of x. And a nicer way to write that would be 1 over 2 times square root of x. So that's our answer. So our derivative in this case is going to be f prime of x is equal to 1 over 2 root x. So just to give a quick example, let's say you wanted to plug in, or let's say you wanted to find the slope of the tangent line to square root of x, f of x is equal to square root of x, at x is equal to 1, you would plug it into your derivative function, f prime of 1 is equal to 1 over 2 times the square root of 1. So apparently that slope is equal to 1/2. So let's look at the graph of the derivative. So this is not really one I would expect you to know what it looks like, but this is what it looks like. So this is the graph of f prime of x is equal to 1 over 2 root x. So again, I just want to point out a couple of different things that we can kind of see going on here. So one thing I just want you to notice is that for your original function, f of x is equal to square root of x, you can't take the square root of a negative number, right? Which is why the graph of square root of x does not include anything over here. It's just only positive numbers and 0. And so similarly, the derivative doesn't have any values on, over here. So another thing is that this graph is always increasing. There is no part of the square root graph where it's going down from left to right. It's always going up. And so what that means is that the derivative is always positive. There's no part of the derivative function that goes below the x-axis, because if it did, that would mean that you would have a slope that was negative. And you know that because the original function is always increasing, there's no way you could have a set as negative. Another thing I want to point out is that, so it's a little bit hard to see here, and we'll get more into this tomorrow, but if you look at what's happening at x is equal to 0 in your original graph, so the closer and closer you get to 0, so if I were to take like a tangent line like here and here and here, and so I can't really draw it because it's too close, they would be getting closer and closer to vertical. So they would be getting steeper and steeper. But the derivative is actually not defined at x is equal to 0, and we'll talk more about why that is next time. But if you look at the derivative, it kind of fits with that, because closer and closer the x values get to 0, the outputs for the derivative are getting higher and higher and higher and higher. And then you have a vertical asymptote at 0, because the derivative function is undefined at 0, right? If you tried to plug in 0 to this, you would get something undefined. So again, we'll get more into details of like why that is tomorrow, but I just wanted to point that out. All right, so that is it for today. So I will give you some more practice with this stuff for your worksheet today, and I will basically be talking a little bit more about kind of relating the graphs of the original function and their derivative in tomorrow's video. All right, thank you.